So understanding ANOVA significance. At the end of calculating an ANOVA, we are left with an F ratio, which we compare against the critical F. Keep in mind, however, that we are comparing multiple groups simultaneously, which means if we find no significance, so if our null hypothesis is true, that all the means are the same, then there are no significant differences between any of the groups. However, if we do find significance in our analysis, we don't automatically know where the significance is. For example, if our analysis contains 3 different groups and our results are significant, we should be asking the question, okay, is the significant difference between group 1 and group 2, between group 1 and group 3, between group 2 and group 3, or is it between all 3 groups, right? We don't automatically know where that significance is, and that's what leads us to using this new tool called the post hoc test. So post hoc tests allow us to determine where a significant difference is in an ANOVA test. They also allow us to control the experiment-wise error rate. And you may wonder, what is that? The experiment-wise error rate is the proportion of experiments in which one or more type 1 errors occur. Remember that as researchers, we are selecting an alpha level that also represents the possibility of us making a type 1 error. And the most common is 0.05, right? For every hypothesis test that we perform, there is a type 1 error rate, and that's the significance level or the alpha. Remember, for our research, especially in this class, we're focusing very heavily on 0.05. However, in the case of an ANOVA, the likelihood of a type 1 error increases. And the reason for that is, think about what happens in an ANOVA, right? If we compare an ANOVA to a t-test, with a t-test, we're only comparing 2 groups. We're comparing group 1 to group 2. We have a 0.05 alpha level, which is the likelihood that we commit a type 1 error. And it stays that way, right? With an alpha of 0.05, as long as we're only comparing those 2 groups, then we maintain that 0.05 type 1 error chance. When it comes to an ANOVA, we're not just comparing group 1 and group 2, we're comparing group 1 and group 2, and then group 1 and group 3, and then we're also comparing group 2 and group 3. So that's a total of 3 different comparisons that are happening. Because it's 3 separate comparisons, the more times we look for significance, the more likely it becomes possible for us to make a type 1 error. Now that might sound a little bit confusing. Hopefully this example that I offer will help kind of make sense of this. So let's say you're rolling a pair of dice. Okay, so a pair of dice, standard pair of dice, you have one die that has a total of 6 sides. Your second die has a total of 6 sides. Let's also say that rolling snake eyes, which means that you roll the dice and you have 2 ones, right? Die number 1 shows a 1, die number 2 shows a 1. That's called snake eyes if you're not very familiar with rolling dice. So let's say that getting snake eyes, getting 2 ones, represents a type 1 error such that rolling snake eyes is something we don't want to happen, right? We don't want to commit a type 1 error. If we roll the dice just 1 time, the likelihood of getting snake eyes is low. However, the more times we continue to roll those dice, the more likely we are going to come across a situation where we actually do roll snake eyes. With enough rolls, it's inevitable. So when running ANOVA, we're not running an infinite amount of tests. So we're not necessarily saying that we are inevitably going to run or going to make a type 1 error within the confines of an ANOVA. However, we must still account for the probability of committing a type 1 error. And that's where this idea of pairwise comparisons comes in. So the formula for calculating type 1 error rate for ANOVA is 1 minus the alpha level up to the C power, and in this case, the C is the number of comparisons being made. I'm introducing you to this formula. I'm not asking you to use this formula. I'm going to show you how this relates to probability of committing type 1 error in just a moment. And so the following table, as I'm about to show you, shows the error rate for various comparisons. Remember, the idea is, group 1 to group 2, that's a 0.05 error rate. But the more times we make comparisons, the more likely it becomes for us to make a type 1 error. And so in this table, we see that happening. In this first row under groups, you see that we have 2 groups. When we have two groups, we only make one comparison, what's happening between group 1 and group 2, and therefore our experiment-wise error rate is 0.05. When we bring in a third group, now we're making a total of 3 comparisons. Oops, excuse me. We're making a total of 3 comparisons, which means that our error rate increases to 0.14. When we introduce a fourth group, we are making a total of 6 comparisons, which increases further our error rate to 0.26, and so on and so forth. As you move further down this table of experiment-wise error rate in this column, you're going to see that you reach a point down by group, having 14 groups or having 15 groups, where you're making so many comparisons. With 14 groups, there's a total of 91 comparisons being made, that your error rate is 0.99. That's almost 100% of the time you're going to make a type 1 error. That's what that's indicating to us. And so that's important for us to understand about what it means to run an ANOVA test. So here is specifically an ANOVA test, but talking even more specifically about the post-hoc test, and that's where this particular table comes in. So this table that we see here is multiple comparisons. This is called a 2-key post-hoc test. I'm going to introduce you to how to ask SPSS to produce this for you when doing your ANOVA analysis. But I want to point out here, make a little bit of sense of what's happening in this table. Remember that an ANOVA test is comparing multiple groups. So with this table, what we are saying is our dependent variable is age and our independent variable is race. Within our race variable, we have each of these categories: Asian, Black and African American, Chicanic, Latinx, Native American, Pacific Islander, white, and other. So in an ANOVA, we have to compare Asian to Black and African American, and then Asian to Chicanics, Asian to Latinx, and so on and so forth. So all of these comparisons are being made. And because our dependent variable is age, what we are asking is, are there significant differences in the ages of our Asian students when compared to our Black students? Between our Asian students, Chicanic students, Asian students, Latinx students, so on and so forth. So we have this mean difference column, we have a standard error column, but what I want to point out here is this significance column. Now, in the significance column, this is what's going to tell you whether or not there's a significant difference between the two groups that are being compared. And you still make the same comparison that we were introduced to within the t-test module, where we are looking for a significance level 0.05 or lower is significant, where 0.05 or higher, well, less than 0.05 is significant, higher than 0.05 is not significant. So if we're looking at this table, this post-hoc table, between our Asian students and our Black and African American students, we have a significance level of 0.023. 0.023 is less than 0.05, which means that there is a significant difference between the ages of our Asian students and our Black and African American students. Moving to the next comparison between Asian and Chicanic students, we have a significance level of 1, which means that there is no significant differences between those groups. Between our Asian and Latinx students, it is 0.04. Therefore, we have significance between these two groups. Between Asian and Native American, it is 0.598. We do not have significance. Compared to Pacific Islanders, 0.99, not significant. Compared to white students, 0.02, it is significant. Compared to other racial identity students, it is 0.34, which is not significant. Now, we don't see the entirety of the post-hoc test in this table here, largely because it's a very long table. This comparison happens for every single group, right? So first we're saying here's Asian students compared to all other racial identities, and then we have Black and African American students compared to all other racial identities, and so this continues all the way down to the bottom of this table. What I want to point out here is notice what's happening between these Asian and Black and African American students. We have a significance of 0.023. That same exact comparison is being made where we are first prioritizing our Black and African American students and then comparing them to Asian students. We still have the same significance level, which means that as we'll learn a little bit more about reporting the results for ANOVA, but you wouldn't have to report this twice, right? You wouldn't say, yes, we found significant difference between Asian and Black students, 0.023, and we also found significant difference between Black African American students and Asian students 0.023, right? You wouldn't make that same comparison. It's still using the same exact data points. So please make sure that when you are reporting your results that you're not doubling up on some of the reports. Okay, so post hoc tests and statistical power trade-off. Post hoc tests are great for controlling experiment-wise error rate. However, an important trade-off occurs. Recall that when a researcher chooses a significance level or an alpha level, they're trading between the rate of making a type 1 error and the significance of difference. This difference is called statistical power. In order for a post hoc test to work, it must lower the individual significance level for each separate comparison. For example, with 2 keys post hoc test, for making 6 comparisons, we actually use an individual significance level that is approximately 0.01 to produce a whole experiment-wise error rate of 0.05. The more comparisons you make, the smaller your individual level significance has to drop in order to maintain a overall test experiment-wise error rate of 0.05. So we just want to keep that in mind. I'm not asking you to calculate the individual significance. This is just important information for kind of understanding the background of how the post hoc tests function.